And then I will talk about some new approaches. The first one is a Lagrange multiplier approach to deal with problems with global constraints. And the next one will be a generalized SAV approach for problems which does not have a gradient structure. So for example, general dissipative systems. And particularly, I will spend some time on applications to Navier-Stokes equations. And I will briefly mention how to deal with bound and positivity preserving problems, and conclude with a few remarks. Okay, so we know that a large class of scientific and engineering problems are modeled by complex nonlinear systems which dissipates or preserve some free energy. And it may also satisfy other constraints. For example, you may have mass conservation, area conservation, etc. Or some quantities, they need to stay in a fixed bound or to be positive. For example, the density cannot be negative, the concentration and cannot be negative, and is within a certain range. So this is very important in practice and in analysis for the numerical scheme to preserve those structures at discrete level. Because at the continuous level, you have those structures, but how to preserve those structures at discrete level, it is usually not an easy task, especially if the systems are very complex. Okay, so I will start with a general gradient system. So what is a gradient system? A gradient system are usually driven by a free energy. So you have a free energy, E phi, and or Hamiltonian if you consider a conservative system. Then the gradient system can be written in this canonical form. So on the left-hand side is the derivative with respect to time. On the right-hand side, you have the variational derivative of the free energy. And then you have a minus G operator in front, where G is a positive operator or a skew-symmetric operator, or it can be a sum of a positive operator and a skew-symmetric operator. So a very important property of this gradient system is that when you take the inner product of this equation with the variational derivative, on the left-hand side, you get the time derivative of the free energy. On the right-hand side, you have this inner product, which you see, since G is either positive or skew-symmetric, so this thing is always less or equal than 0. So that's the energy dissipation or energy conservation. So there are many, many, many examples. So some well-known examples are Allen-Kahn equations, Cahillian equations, phase field models, liquid crystal models, superconductivity, image processing, and lots of optimization problems. Those are dissipative systems. And you could also have a conservative system like nonlinear Schrödinger equations, Sine-Gordon equations, etc., etc. So over the years, there are many, many papers and work devoted to design numerical scheme which can preserve the energy dissipation of the gradient system. And there's a large number of work which I guess I will skip. So if you're interested, you can look at the reference presented here. So for the constraint of time, I will move on to the new approach. So I will start with the original scalar auxiliary variable approach. And the guiding principle of this approach is very important. So it's any implicit global property, you no matter what kind of property, so the energy dissipation is a global property, and the mass conservation, it is also a global property. So any implicit global property, you can enforce them at the discrete level by introducing a scalar auxiliary variable. Okay, so that's our guiding principle. So if you want to preserve energy dissipation, what we can do is we just introduce what we call a SAV. So how do we do that? So suppose I write my free energy as two terms. Y is the linear term, the quadratic term, and the second part is the rest. So it can take any form. You only need to spare apart a quadratic form as a first term, and you denote the integration of the second part as E1, and you assume this E1 phi is bounded from below, because this is a free energy. So usually this condition is satisfied, and then we can introduce one SAV, which is just a function of time. We denote by RT to be the square root of this E1 plus a constant C0, so that the sense under the square root is always positive, so it's well defined. And then I rewrite my free energy. You see, for this part, for E1 phi, I rewrite it as R squared minus C0. And then I can rewrite the gradient system into an expanded system by adding the energy dissipation equation, not the energy dissipation, by adding the equation for the SAV variable to the system. So so first we rewrite the equation by introducing an intermediate variable mu, which in material science is called chemical potential. This is just the variational derivative. And you take the variational derivative of this thing, you end up with a term like this here. The first term gives you L phi. The second term gives you F prime phi multiplied by a factor here, which does not exist before. But you see, what is this? This is RT divided by the square root, which should be identically equals to 1. So this is equivalent to the original system, right? Exactly equals to the original. And to get an additional equation, you take the time derivative with respect to R here. You get this. You get this ODE, but it's a non-local ODE. You get this non-local ODE. Okay, instead of discretizing the original system, and now we are going to discretize this expanded system. And why do we want to discretize the expanded system? Because we now have a little bit more flexibility. We have an extra variable, and we can use this extra variable to enforce the energy dissipation. So that's the idea. Okay, so a very simple way is a second order scheme. You can use any type of second order here. I take a very simple one, the Crank-Nicolson. You treat all the linear terms implicitly. So here n plus half is the average of step n plus 1 and step n. And all the nonlinear terms, you treat them explicitly. So anything with a phi tilde is a second order extrapolation. So you see, those terms are treated explicitly. And for the equation for R, you do the same. For the nonlinear term, you treat it explicitly. And so that is the linear scheme. That is our scheme, which is linear. But what type of property it has? And you take the inner product of the first equation with mu n plus half. You take the inner product of the second equation with negative of the time derivative. And you take the inner product of the third equation with 2 times Rn plus half. And then you sum up the results. You see whatever the nonlinear term, the contribution from the nonlinear term here will cancel with the nonlinear term here. So you end up immediately this energy conservation. You end up exactly with this this energy conservation, which is the same energy identity as the continuous system. And so here, this is the modified energy, right? So we have Rn plus 1, which is an approximation to E1. So the modified energy at step n plus 1 minus the modified energy at step n is always negative. So you have unconditional energy stability. So that's the nice thing. And so why you could have unconditional energy stability compared to the usual semi-implicit scheme. So what is the usual semi-implicit scheme? Usual semi-implicit is you treat this exactly the same, and you don't have this term, right? You just have f prime, and you don't have the red equation. So you can eliminate Rn plus 1 from the previous scheme, and you find out this is our. Can someone clear up this? Someone is writing on the screen. I don't know why. Okay, anyway. So once you eliminate Rn plus half, you end up with this equation. You see the extra red term adds stability to this semi-implicit scheme. And why it adds stability? Because when you try to prove stability, you multiply the equation by phi n plus 1 minus phi n, and you get this term multiplied by phi n plus minus phi n is positive. You get a positive term here. And so that's why it is a stabilizing term. And so how do we actually solve this coupled? You see, this is a coupled linear system. How do we actually solve it? You can solve it very easily by writing phi and mu as a linear combination of Rn plus 1. As a linear combination of Rn plus 1. And of phi 1, Rn plus 1 plus phi 2, and then you plug in this equation, you plug in this relation into the first 2 equations, and you collect the terms without Rn plus 1. You get the equation for phi 1 and mu 1, which is just a semi-implicit scheme, linear, constant coefficient. And you collect all the terms with Rn plus 1, you get another equation for phi 2 and mu 2, which is also a linear equation with constant coefficient. So those equations are very easy to solve. And once you solve the phi 1, phi 2, and then you plug this equation again back into this red equation. And then you get just a linear equation for Rn plus 1, which you can solve directly. So the total computational cost is just solving this two linear system with constant coefficient. So it's very easy to solve. It's very easy to solve. And I will mention just a little bit about the convergence and error analysis. So now there are complete convergence and error analysis available for a large class of nonlinear systems with different kind of nonlinearities, with different kind of spatial discretizations. So I forgot to mention that I will mainly concentrate on time discretization scheme, but whatever I present here is applicable with finite element, spectral method, spectral elements, and also with finite difference if you use summation by parts formula. So it is very general. You can apply it to many different kind of spatial discretization. The proof of stability is essentially the same, but of course, for the error analysis, you have to do it case by case. So we have done it for just time discretization, finite elements, and finite difference, and many other systems as well. Okay, so I will mention a little bit. So this seems to be a little bit too good to be true, right? You have a linear scheme which is unconditionally stable and have all the properties seems that you'd like to have, but you have to remember that the unconditional stability does not guarantee good accuracy when you choose large time steps. So if you want good accuracy, you may still need small time steps. But what does unconditional stability give you? It gives you the possibility to use adaptive time stepping. And also another way to increase the efficiency is you have to split your free energy in a proper way. So you remember I said we have a free energy and we're going to split into two terms. One is a quadratic term and one is the rest. But you have different ways to do this. For example, this is the usual free energy for Alan-Kahn and Kahiliya phase field equations. And you have a small constant, one over large constant, 1 over epsilon here. So if you treat this term explicitly, you will need a very small time steps to get accurate result. But you can fix this very easily. What you could do is you can add and subtract a quadratic term here. You add a quadratic term to the implicit part, and of course you need to subtract it. And you can still prove this is bounded from below. And why do we do this? Because we need this term to balance the nonlinear term. And S just shows to be any constant, although one constant would be fine. And if you do this, then the numerical scheme becomes very accurate and stable. So for example, if you do the usual splitting, with large time steps, you see you are going to get oscillation and non-accurate results. And with small time steps, you get accurate results. But if you do the proper splitting like in the previous slides, then even with very large time step, you get accurate result. So that's the first strategy. The second strategy is you need to do adaptive time step. And you see we have this SAV variable R, which is supposed to be the approximation of square root of E1 phi. But once you started the numerical numerical scheme, this ratio Rn plus 1 divided by this, they can change, right? If a time step is small, they are going to be very close to 1, and this is good. But if you choose large time step, and it may go away from 1. Once it goes away from 1, it simply means your scheme, numerical scheme, is not accurate. It is still stable, but it's not accurate. So this thing here, this ratio, is just one indication of whether your scheme is, your time step is sufficiently small. And if you add it compared with combined with another time stepping strategy, then you can get a very efficient scheme. So here's a very complex simulation of Cauchy equations. You see the free energy. This is the free energy, and during the evolution, there are many sudden energy drops. And here is the time step of the adaptive time step. You see, at the beginning, you need really very, very small time steps. And each time when the energy drops very fast, the time step requirement, you need to require the time step to be very small. But at other times, you can choose much larger time step, 2 or 3 orders of larger than the smallest time step. So by using adaptive time stepping, this can be very efficient. Okay, so that is the original SAV, and now what do we really need? We would like to have in addition. What additional properties do we like to have? So you see, for the original SAV, we need this to be bounded from below, and this may not be possible sometimes. And we'd like to satisfy other global constraints. And so for the original SAV, it requires solving 2 linear systems. Can we just solve 1 linear system? And for the original SAV, we can only prove that the second order scheme is energy stable. But for higher order scheme, we cannot actually prove multi-step scheme. We cannot prove it's unconditional energy stable. And we'd like it to be applicable to general system without gradient structure. And also maybe can also be positivity and bound preserving. So those are other desired properties. And I will present 2 approaches which can satisfy many of those requirements. So the first one is how to deal with other global constraints. Suppose I have a free energy. Instead of minimizing the free energy, I also have other constraints. So this is a constraint optimization. So for the sake of simplicity, I consider one constraint first. We can deal many constraints. Suppose I have a global constraint where h phi is some integral. And the idea is still the guiding principle of the SAV. For any global property, you can introduce one scalar variable. And here we are going to use a Lagrange multiplier, lambda t, to enforce this global conservation. And so this is, you introduce a lambda t to enforce this, but you also would like to satisfy the energy dissipation, right? It's a gradient flow, you have energy dissipation. So we are going to introduce another Lagrange multiplier, eta t, to enforce the energy relation. So to enforce, so we add another equation with respect to the nonlinear part of the energy. And you see, you take the time derivative, you should get this to be f prime phi times phi t. But I'm going to multiply in front a eta t, and eta t is the same eta t here, which at a continuous case, this should be identically equals to 1. So it does not change the equation. And I add a red term here, which is identically equals to 0 because of this conservation, right? So delta h delta phi in the product with phi t should equals to 0. And why do I need to add this 0 term? It's because when I discretize this equation, I need this term to balance this term, and I need this term to balance this term. So with eta 0 equals to 1, so you are going to get the exact solution of this equation is for eta t is identically equals to 1. And for lambda t, it depends whether this constraint is an implicit constraint or not an implicit constraint. For example, in the nonlinear Schrodinger equation, the mass conservation is implicit, then which means this lambda t is identically equals to 0. If it's not an implicit constraint, then lambda t is Lagrange multiplier. So how do we discretize this expanded system? We do exactly the same thing as before. We treat the linear terms implicitly. We treat all the nonlinear terms explicitly. And of course, the Lagrange multiplier eta and lambda is implicit. And then we enforce exactly this conservation, and we approximate the energy conservation equation by this second order scheme. So this is the second order Crank-Hillier equation, Crank-Hillier scheme, and you can prove easily, just like before, the energy law is satisfied unconditionally. And this time, you actually get the exact energy, not the modified energy, because you see you have the exact energy. You get the exact energy conservation or dissipation. So this is very nice, but you see, this is a nonlinear equation now. And here is a nonlinear equation too. Those are linear equations, but those two are nonlinear algebraic equation. Here is a linear differential equation. So this is a coupled nonlinear system. And how do we solve it? If you cannot efficiently solve it, then it's useless, right? Even though it satisfies the energy dissipation. Fortunately, this can be also easily solved. You also do the similar trick. You write phi as a linear combination of the Lagrange multiplier. and the mu as a linear combination of the Lagrange multiplier. And you plug in those two into just the first two equations, the linear equation. And and then you get you collect all the term without the eta and the lambda. You get a linear equation for phi 1, and then for eta you get a linear equation for phi 2 mu 2, and for lambda you get a linear equation for phi 3 mu 3. So you just solve 3 decoupled linear equation with constant coefficient at each time step. And once you solve this, you plug in those two relation back into the red equation here, and you end up with two nonlinear algebraic system for eta and lambda. Remember, eta and lambda is just a number, so it's a nonlinear algebraic system. You can solve it with a Newton iteration with essentially no cost, right? It's just a 2x2 nonlinear algebraic equation. So once again, the scheme is very the scheme is very efficient and easy to solve. But there are some difficulties with this approach. Is for the nonlinear system, even though it doesn't cost you much to solve, but it may not have a unique solution, right? So, and it may not have a good solution. So for this, you may need a smaller time step for the nonlinear algebraic system to have a sensible solution. And also it is a little bit more difficult to analyze. But the idea is quite general. It can be applied with a problem with many global constraints. So if you have a problem with for example, for Hamiltonian system, you want to enforce multiple Hamiltonians, and not many scheme can do that. This is one of the scheme which can enforce as many Hamiltonian as you like. And here's I guess due to time constraint, I'm going to skip this example and go to the next approach. Is for general dissipative systems. So now we are going to consider a general dissipative system like this, where A is a positive operator and F is a nonlinear term, which could be semi-linear and quasi-linear. And we assume this system has an energy dissipation, but it does not have a gradient structure. It is not a gradient. It only dissipates some energy where G is a positive operator here. And of course, we can assume this energy is bounded from below. And so the guiding principle is still the same. We are going to introduce a SAV, and this time I just let this SAV to be the energy plus this constant. And we are going to expand this original PDE by adding this energy dissipation to the system. So since R is just I is just this energy, so you can write the dE dt as dr dt, right? And in front, just like before, you stick a ratio RT divided by E, which be identically equals to 1, right? Okay, so this system is equivalent to the original system, and now we are going to discretize this expanded system. So Now we are going to take a quite different approach. You see, before we always use Crank-Nicolson or some type of other PDF scheme. And here we're going to use a sort of a predictor-corrector approach. And I will explain a first order scheme, how to do that. So first, I'm going to solve a phi bar, which is a prediction, by just solving a semi-linear equation, right? I treat nonlinear term explicitly. Once I get phi bar, I solve, I discretize the second equation for the energy, and you see, this is just a linear equation for Rn plus 1, which you directly solve. And once we solve R, I compute C to be this ratio. And finally, I do a correction to phi bar. And C, remember, C is approximation to 1. So 1 minus C is order delta T. And so phi n plus 1, I use a second order correction to phi bar. So when I plug in phi, when I replace phi bar by phi here, I still end up with a consistent first order approximation for phi n plus 1. So that's the scheme. And the scheme is extremely simple because you really need just to solve this first red equation, which is a linear equation with constant coefficient. And we can do high order as well. So now let's use a case order BDF implicit explicit scheme. So the nonlinear term, I'm going to use a case order extrapolation. And for the linear term, for the time derivative, I use BDFK. So I first solve phi bar, which is a prediction, by solving a semi-linear equation. Once I get phi bar, okay, the rest is exactly the same as before, as the first order equation here. So here the key point is I still use a first order approximation to the energy. To the energy, I still use first order approximation. I still compute C, but now in order to keep my case order accuracy, I do a K plus 1's order correction. I do a K plus 1's order correction here. Okay, so once again, the scheme is very simple, right? You just need to solve one equation. The rest, there's no equation to solve. Okay, so what type of property do we have? We can show that the scheme is unconditionally stable. In what sense? In this sense, Rn plus 1, we know is an approximation to the energy. So if Rn is positive, then we can show Rn plus 1 is positive and C is positive. So you have this energy dissipation with the modified energy. But this thing does not really tell you much because this R is just a number, which is approximation to the energy. It does not contain any norms. But if you write your free energy, split your free energy into two terms, one with a quadratic term like this, then you can prove for the norm induced by this linear positive operator, then you have this norm is unconditionally bounded for any delta t. So usually this is a Laplacian, so you have H1 norm is uniformly bounded. So now this is a high order and a uniformly bounded scheme. And you can also derive, we can also derive error estimates, but the error estimates is restricted to the order less or equal than 5. And for For k less or equal than 5, we can prove that the error of phi bar and also phi, both of them are case order approximation. So this is very nice. And in fact, right now, this result can be extended to order 6 by using a new stability result recently obtained by some other people. Okay, so here are some numerical tests for Crank-Nicolson equations. You see first order, second order, third order, fourth order. So there's no problems for the accuracy. And so now I will spend. Why do I always have? Okay, now I will spend some time to talk about the application to Navier-Stokes equation. So we know that the Navier-Stokes equation is a dissipative system, but it's not a gradient flow, and it has many. It's a foundation for computational fluid dynamics. So for incompressible fluid dynamics, right? So we need to. It's very important to have an efficient and accurate scheme. So let's. So this is a Navier-Stokes equation. You have a vector unknown u and scalar unknown p, which satisfy and your velocity is divergence free. We consider periodic boundary condition first. Then you can replace the divergence free condition by taking the divergence to the first equation. You get a Laplace equation for the pressure, like this. And since it's a periodic boundary condition, pressure is also with the periodic boundary condition. So you can replace this by this. You cannot do this if it's a non-slip boundary condition, because then we don't have a pressure boundary condition. So we know that the Navier-Stokes equation is energy dissipative, with the energy given by this. And so we can do this scheme very easily, right? We can just apply the previous scheme for general dissipative system. You treat the pressure and the nonlinear term together explicitly, and you solve a U bar first. And then once you get a U bar, you solve Rn+1 from here. And then you compute C, and then you do a correction to U bar. And once you compute the UN+1, then you solve a pressure Poisson equation, right? So the total cost is solving this equation here and solving this equation here, which in the periodic case, if you use a Fourier spectral method, there's it's all diagonal system, no equation to solve. So it's very, very efficient. And you can prove, so you can prove the following stability result, and you can also prove for a Fourier spectral method, you can also prove the optimal convergence with respect to time step, and with respect to the number of Fourier modes. And here, K is the order of the scheme, and M is the smoothness of your solution. Is the smoothness index. So for 2 dimension, 3 dimension, you have slightly different results. For 3 dimension, we only have local convergence and local error estimates. This is because for the 3 dimension, we only have local existence the exact for the strong solution as well. Okay, so numerical test. First of all, it's accuracy test. That's of course no problem. And then we do a benchmark test, a very complex rotating flow, a benchmark test. So this is the vorticity of the flow at time t at 1.05. And so this problem at around t equals to this time, it has a very complex structure that if you use a semi-implicit scheme with this parameter, it blows up. It blows up, it cannot continue. But with our SAV approach, and you see we have this factor here, right? We used a third order scheme. We have this SAV factor, which is supposed to be a very good approximation to 1. So, but at this point where the semi-implicit scheme blows up, it has to adjust the SAV factor a little bit, it drops a little bit, so that it can compute past this difficult time, and it can continue. So it is so this proves that SAV scheme it's more robust than a usual semi-implicit scheme for this complex situation. And here is an example showing higher order approximation for complex, for very complex flow. It is much better than lower order approximation. So we know that the SAV scheme will always give you a stable solution, but it does not guarantee a good solution. So you see, here's a first order, second order, give you garbage. But if you use a third order and the first order with the same parameter, you get the correct solution. And so later we're going to see, now we're going to see many examples where the third order scheme is actually the most robust for very complex nonlinear system. So I still have a few minutes. Let me talk about a little bit for maybe a Stokes equation with Dirichlet boundary condition. So with Dirichlet boundary condition, the difficulty is we don't have a pressure boundary condition. So you cannot really solve a pressure Poisson equation in the strong form because there's no boundary condition. So we couple this SAV approach with the consistent splitting approach, which we developed some years ago, that goes like this. So for the nonlinear scheme, so it's similar to the periodic case. The first step is exactly the same. You nonlinear term and pressure, you treat them explicitly, and you solve U bar first from this equation. And then you solve Rm plus 1 from here. Okay, so here, if you have external force, you can add external force without a problem. And then you do a correction to get the U bar. So the difference is at the last step. For the last step, you see for periodic case, you solve a strong pressure Poisson equation. But for the Dirichlet case, we are going to solve a pressure Poisson equation in the weak form with a modified boundary conditions. You see, the correct boundary condition here should be the Laplace U, but if you use Laplace U here, then the scheme is unstable. you have to use you have to use we know that Laplace U equals to grad D equals to gradient times gradient then divergence plus minus curl. So you should drop the gradient divergence term because you want the inverse divergence U equals to 0. So by modifying this boundary condition, so UN plus 1 is computed from the previous time step. And then, so this is just the pressure equation, pressure Poisson equation in the weak form. And so for this scheme, you can also prove the same result as before. Actually, we cannot. We prove stability as before. The error analysis is a little bit more difficult because of the Dirichlet boundary conditions. So the error analysis is still in progress. But anyway, we have applied this scheme to solve a very complex rotating flow. So here's a Navier-Stokes rotating Navier-Stokes equation. So the difference here with the usual one is you have a Coriolis force, and so it has a very important application in planetary and geophysical science, where this omega 0 can be this rotating speed can be very, very fast. So the previous scheme was limited to a rotating speed about 10 to the 7 because it required very small time step and for the numerical scheme to work, for previous numerical scheme to work. But now with our scheme, so this is okay, this scheme is a little bit hard to explain, but we just need to look at this number and this number here. So, and this is a number of time steps per Forsen period. And so here is the new third order SAV scheme with 100 time step. We get the same accurate result as the previous second order scheme with 800 time step. So you can increase the time step 8-fold and while still getting more accurate result than this result here. And by doing this, we were able to extend the range of the parameters that we can deal with. So this is still a preliminary result. We computed some result with the rotating speed to be an order of magnitude more than previous available. You see the very complex symmetry and structures here are well captured by this third order scheme with the spectral discretization. Okay, I think my time is up, and so I will not talk about the bound and the positivity preserving. So this requires another lecture. So I'm going to conclude. So we presented the SAV approach, which allow us to construct efficient and accurate scheme for a large class of complex nonlinear systems. So the good thing is that it only requires solving linear equation with constant coefficient. So it's very easy to implement. And it's extremely efficient if you use a spectral or finite difference method where the fast solvers are very important to you. And it can be high order and unconditionally stable. And it can also satisfy global constraints. And it can be used with almost any consistent Colloquium type spatial discretization. And so if you are interested to know a little bit more, so here's a couple of papers for your reference. And So I'm going to stop here and thank you for your attention.
All right, thank you, Prof. Jie Shen, for this very interesting, informative, and a very comprehensive talk. Yeah, you can give many recipes you can cook up with, but you may take some time to digest. All right, so now it's time for questions. So if you have questions, now you can unmute yourself.